Hello everyone, how's it going? So today we're going to do a quick YOLO object detection on images using just your CPU. You're not going to be using any external hardware. This is just running on a plain CPU, and my CPU is running on a very low speed. So I mean, if it's working on my computer, it should work on any computer. So trust me, but it's pretty easy. It's very easy to implement. You can see some outputs here. So it's detecting a board, it's detecting the monitors, it's detecting the chair, keyboard, mouse, some books, the water bottle, cell phone, Apple, the chairs, people, everyone in this image with the bird on top. So it's pretty good, it's pretty fast, and it's very easy to implement. We're only going to be using two libraries, OpenCV and NumPy. So I'll show you the quick introduction of YOLO. So YOLO, it's nothing but stands for you look only once, and it's designed by this gentleman, and this is his GitHub account, PG Ready. His name is Jason. Let me open up his main page. So you'll see this is the gentleman. I'm sorry, did I say Jason? It's Joseph Redman, and he and his team had developed this YOLO object detection, and we'll go back to this. So what it does is basically it divides the image into boxes, these small boxes. I don't know if it's visible here. So it divides these images into small boxes and then feeds it to the neural network, and from those boxes it identifies the maxima and detects where the objects could be, and then identify for object detection. So unlike other image recognition or image object detection algorithms, the ResNet, this does not pass through the network multiple times, so it only goes through once and identifies the objects based on their maxima. The trade-off with this guy is it's not very accurate. Since it's efficient, it's fast, but it's not very accurate compared to the ResNet. But it does the job. It's able to pretty much identify the main common objects, and it's trained on a variety of sets. They have libraries where you can train your own data set, but we are going to be using a pre-trained data set here to implement YOLO, and I'll quickly go into that. So we saw how the images are being detected here, how the boat and all these images are nicely being detected. What you need to do this for is install OpenCV, and you can come here and just install pip install OpenCV. Just copy this guy here and then go to your command prompt. I'm using a virtual environment, and I named it YOLO here, but you can, if you don't know what the virtual environment is, it's pretty easy. Just Google it, and you can use it by virtual env, or if you're using Windows, you can use Anaconda. But it's pretty easy. If you have any doubts, leave a comment, and I'll be happy to help you. So just save, and you can do pip install OpenCV. So this is one library, and the other library is going to be pip install NumPy, and this is just for mathematical and array computations, and OpenCV is for image computations. So these are the two only libraries that you need. We are not going to be setting up any complicated neural networks. OpenCV allows us to read the neural networks which are already pre-trained. So you're implementing OpenCV and NumPy, and you're going to be implementing one by one. So I'll go into each details. Let me comment off everything so it doesn't confuse you, and we'll go and uncomment each one as we go. So let's start from here, and you're importing two libraries, which is OpenCV and NumPy. So OpenCV is used for image computation, and NumPy is just used for array computation. Nothing too crazy in that. The first step is to read these two files, the weights file and the configuration file for the YOLO, and it's something which should be available in your directory, the same directory where you are. So here in my case, YOLO v3's configuration and YOLO weights. These two are available on GitHub on their own page in the PG Ready on this guy's GitHub account. which is GitHub PG ready YOLO, and it's available there, but if not, I'll be uploading it on my GitHub also, so you can take it from there. But it's pretty much these three files. So these two are for YOLO, and this is the array list or the class names. So if I open this guy here, Coco names, so Coco names is nothing but it has all the classes of different objects that they had trained the algorithm on. So you can see about 80 objects in this name, and it has been trained on these objects. So it's nothing but defining that these are the classes that are present in the Coco names, and that's what the YOLO is going to be detecting. So once you read YOLO v3 configuration and weights, this is a deep neural network library of OpenCV, and it's nothing but reading the pre-trained weights and configuration of that network at which YOLO was trained by the original people, and OpenCV is just importing those configurations, and we're saving it under this network called YOLO. So this is nothing but the convolution network at which YOLO object detection was trained. So once we do that, we are defining the classes. This is nothing but to read the Coco names. We saw what Coco names is here. So let me open it again. The Coco names is nothing but just defining all the objects, and we're just reading that file here, and we're going to be saving it under this array called classes. So let's see how we're going to be doing that. And we're opening Coco names, and we're opening it under read mode, and we're opening it as a file here. And once we read it, we are first stripping all the words of any spaces. So if you see here, there is space around here. There's unwanted space, unwanted matter, which we don't need. So that's the reason we are doing the strip, so you can remove the spaces, and then it's reading each line by line in the file, and then saving it as an array element here in the classes. So each word here in Coco names is going to be imported, extracted, and it's going to be saved under classes as an array. So once that is done, we want to extract our YOLO network. So the network which we defined here, we're going to be extracting that, and there are two main extraction things, and that's the one is the layer names, and the other is the output layers. And this is nothing but it's defined specific to those to these guys here. So it's defined specific to the configuration and weights at the neural network which the original file was trained, and you're just extracting the layered names from there and the output layers. So if let me scroll here to see how it goes through. I'll also putting it in the GitHub so it becomes easier for you to copy and utilize this in your code. Again, this is just my implementation. It's I did not make this code, so it's available freely on GitHub by other programmers and developers, so we can use theirs, and I'm just showing my implementation. So this is output layers, and we define all the output layers in this file, and we keep it safe. Here I'm just defining two colors because I'm using the color red for writing the font and color green to highlight where the objects are. So this is just to define the colors, so we can, when we draw the rectangles on the image, it can use these color profiles. So once we are done with this, we're going to be loading the images. So I'm giving the name image, and image is nothing but the image that is saved in the same directory. So see, if this is the Python file which I'm editing right now, and this is the image, so both of them should be in the same directory. If not, you need to provide the directory path file so it can read exactly where it is. So this is the image that we're going to be providing to the application, and it's going to be reading from here. So we are saving name, and we're just calling the image here, and by using OpenCV IMRead, it's going to be reading the image file from the directory, and it will extract the image. But we also are interested in the height, width, and the channels of the image. Channels not so much, but height and width is more important because we want to identify the height and width, because the network which was trained here, it had its own height and weight, height and width of the image, and we want to replace and compress the image into that same format which they had trained. This is the next step where we are using blob from image, and the reason we do blob from image is interesting because every image is different. I mean, in an image which you say, say example, the apple here. So if I take the picture apple, and if I open the apple in case of in bright light, it's different. If you take the apple in a different environment, you take it to your kitchen, you take it to your living room, you take it to you take it outside and take the picture of the same apple, that apple will look different in different environment, and that is solely because of the light and intensity which is being reflected on the apple. So that causes too much of issues when doing image processing. So that's nothing but noise. Even though it's the same object, even though it's the same apple, but it'll look different in different light, in different scenarios, in different circumstances. And there are many other parameters that come into place: the aperture, the camera, the type of camera you're going to be using. So everything that it affects a lot. So in order to remove all those dependencies, we used blob from image. So what it does is it removes the image and it takes the average of the image. So it comes down to the basic minima or the medium of the image, and we use the media which the original guys had used, and we just plug in those same numbers so that we bring our image to the same level of the original image which the YOLO object detection was trained. So we are doing nothing but bringing our images which are in different light, different scenario. We are in a different test environment, and we're just bringing those images to the original network parameters. So the detected, so the convolution network doesn't feel different, and there is no errors in the detection process. Once we do that, we are going to provide that image, and we're going to be creating this output layers using the forward network, and it's nothing, it's going to be reading the network, the YOLO network, and it's going to be saving it under this outputs file. Once the outputs is identified, now we're going to be using that to detect our images. So we're going to be using the blob is where all the image is present, and we are going to be passing that to detect the images. So we are going to provide the class IDs. This is identifying the different classes based on the COCO names. So we are going to be identifying the different objects that are different types of objects that are present in the image. And confidence score is it helps us to remove noise, because the object detection module detects many other objects, not just it can identify many things as objects, which is nothing but error, and we use confidence score to remove or suppress those noise features. And boxes is defining where is where we are going to be defining all our detected objects from the image. Now this is where the detection happens. So we are going to be using the detection here, and we are saving all the outputs are going to be saved in the output here, and it's going to be saved here under output. We are now going to start the detection process. For detection in output, the scores, we are now starting to make sense of all these scores that are going to be detected from these images. So this is just nothing but pre-training all these images. So let me uncomment all of these so we can go all of this together. Okay, Okay, so we are now here into the for loop. So for output in outputs, for detection in detection output, now we are going to be reading each output, each class variable, and identify in the image, but also assign a score so that we can identify only those core values which are important for us. So this all set is used for confidence scoring. So the NP argmax is only going to take the maxima of that scores. So all the detection that was performed, it's going to only take the maxima of that score and provide the class ID. And this is our confidence. And even in the confidence, we are only going to be using those confidences that is more than 50%. So 0.5, if only the confidence is greater than 0.5, we are going to be using that. And here we are defining where these objects are. So we're defining the x value, the y value of the object, and this is defining the original network detects and identifies the center point of that object, and it is stored in center X and center Y, but OpenCV needs the top left corner of the box. So OpenCV has a different coordinate structure for images, and for that purpose we take the center of the object and move it to the top left corner by using this command. So we subtract the x by width and then divide it by 2. So we want to divide the width by 2. Sorry, first we need to divide the width by 2 and then subtract the center value of x by this, so it takes it to the x value. Similarly is the y, where we are going to be defining the half of the height and then subtract the y value from the height, so it takes from the center to the top left corner of the box. So imagine, let me open up one of the images, detected images. So imagine this is the center, center X and center Y. So we want to go to this particular corner of this box. So center X minus half of the width. So this is the whole width, but we are going to be only using the half of the width. So center X minus width, which will be here, and the center X value, which whatever it is, it's going to come here. So that's the X region, and the Y region is nothing but defining the subtracting the Y from the half of the height. So the half height is, so this is the height and the half of the height is somewhere here, and Y is here. So we are subtracting Y from the height and we come here. So that's how we are going to move the coordinate from the center of the box to the top left corner, and these two other functions. We are then also using, so the detection has 4 arrays, 0, 1, 2, 3, 4 elements in the array, and the first and the second element is the width and the height. The second and third element multiplied by the width and the height gives you the width and the height of the box. So once we know where these boxes are, where these elements are, we are defining them and we are saving it into an array called boxes, which we defined here, and we are saving all these boxes and we are appending them, all these coordinate variables x, y, and wh. This is what we need to in order for us to draw the object. So we are going to be just appending the box array. Once we do that, we use the confidences to also at the same time store the confidence value, and the class IDs are appending. Again, we are also, because we just don't need the boxes, but we also need to identify what that object is, whether it's a box, whether it is a boat, a person, a ship. So all those class IDs are saved here. So we are appending all of these into these 3 arrays. Once we do all these 3 arrays, we are coming back here. We are using the indices, and this is non-maxima suppression. So OpenCV, the deep neural network, has the non-maxima suppression function. So what it does is, the boxes that are detected here, it detects everything. It detects arrays. There are a lot of errors which are being detected in the image. So imagine, for example, in this case, now it's detecting everything in this. It's detecting the monitors, the keyboard, the mouse. Almost everything is being properly detected. But what happens is there are times that OpenCV or the deep neural network causes too much of error, and it could detect this white box as a wall, and it might detect this wall as some sort of color or gradient. Some unnecessary detection happens, like these objects here, these error particles. These are nothing but noise, and the neural network tends to detect those objects as well, and we don't want these objects to be detected here. I mean, I did not show how it would be, but if we did not use the non-maximum suppression, then you would see a lot of noise here. You will see more than 3 boxes here and more than 3 objects, and it will detect many other items here as objects. So that's nothing but error, and we want to suppress that by using non-maxima suppression, and this is the function to do non-maxima suppression. Once we identify the non-maxima suppression, then we simply use OpenCV to draw the boxes, the end of the boxes. So we have removed all the unnecessary items, and now we are only going to be detecting those boxes that are exactly correct. So we have the indices of only those boxes that are important, and we are now using them. So only those indices where the boxes are very important are going to be used, not every element of the box. So only those boxes where after non-maxima suppression where the boxes were detected are only going to be used. So say for example, for us to quickly test, let's do this thing. I will remove this. I'll avoid the IM show so we don't print it on the image, and I will also remove this function. We will also you know what, let me keep the IM show so we can stop the program for a minute, and we will quickly do a thing here. So let's do print length of boxes, and quickly do print length of indices. So let's see if it has any difference. Most likely it may not have, because there is not much of objects to be detected, but let's see. I'm coming here, and let's print. Let's wait for it to detect. So some error is coming up here. We did not even set this guy here, so I'm glad we ran that. So I forgot about uncommenting this part. So because they are passing the image blob, and this is the blob image that we had detected, and we want to pass that to the network, so where the YOLO network can use that blob image to detect. So that's the reason it was throwing that error. But now since we fixed it, let's save it and let's go back and run. We'll clear and we'll run Python object detection from images cpu.py, and then let's give it a few seconds, and it's giving us the indices. So the length of the initial boxes was 4, but the length of the indices is only 3. So it most likely detected one more error, and the non-maxima suppression removed that error for us. Now let's come back here, and we will come back to our original where we were. Okay, so we are coming back here. We did the printing of the boxes and indices to see how the non-maximum suppression is helping us, and let's remove that. And now we are just going to be drawing the boxes around the object. So we can see the output of the function. So we are using the length of the boxes and the length of the indices to maneuver through each boxes, and then only use the ones that we are interested in by referencing the non-maximal suppression indices. And we are again using the XYWH of the boxes. We are just extracting the coordinates in the width and the height, so we know how big our box is and where the boxes is. The label is extracting the text from the classes, and it is referencing the Coco names here, and whatever object was detected is just passing into the label, so we can write the text by using the CV put text. And CV rectangle is nothing but drawing the rectangles. So if you can see here, CV rectangle, we are passing the image, we're passing the XY coordinates, and we're passing the width and the height of the coordinate, the end coordinate. And I'm giving the green color which we had defined earlier, and the thickness of the box. And once we draw the box, we are putting the text, and we are putting the text on the same IMG image. We are passing the label, what text we want to put down, by passing the label variable here. And we are defining where the text should be present. So I'm defining that it should be on the same X and Y coordinate, but shifted by 10 pixels on the Y axis. And here I'm using the font that has to be detected. This is the size of the font, the color of the font, the thickness of the font. So we define all these parameters to write down and then draw the rectangle using OpenCV. And here we just show the image. We show the image and we also write the image. So let's write the image as, we'll write output.jpg, and we just save here. So we will uncomment this part because the image is too big for my laptop screen to show. So we're just going to be writing it for now, and then visiting the image from the file explorer. We're using CV wait key so that we can display the image, and once everything is done, we destroy all the images, all the windows. But since we are not going to be using IM show, we don't need this guy, and we don't need this guy. So we just close this and we run the program. I think this program is already running, so let me close this and then open Python object detection from images CPU. So it looks like it ran successfully, and we should have the image output.jpg out here. So you can see it has detected the bottle, the apple, the cell phone, and it's detecting it perfectly. So with that, we come to the conclusion of this application. I do want to explain that YOLO detection is something which is very popular because of the speed of implementation, and it can be implemented on Raspberry Pis, on very cheap computers, easy and very less powerful computers, and hence it's being very widely adopted, and it's very accurate compared to the previous object detection libraries and modules that were available. There are many other YouTubers and many other profiles. Many of the people who are implementing this. PySource is one gentleman who has his own YouTube channel and website, and Adrian from PyImageSearch.com. He is another gentleman with quite a bit of work on YOLO and other types of different object detection. So just wanted to give reference to them. They have done much better work on this. So if you want further explanation, you can always visit their websites, and in the coming days we will come up with our own implementation and our own ideas around the YOLO object detection. So if you like this video, leave me a comment and let me know, and if there's anything that you're particularly interested in, leave a comment and subscribe to the channel if you want to follow along my journey through computer vision, AI, and IoT. With that, I say goodbye and stay safe.